So today we are talking about ice tables that involve coefficients, and we're also going to talk about Le Chatelier's principle. You're going to see both of these in your homework. You're going to see one on quiz. You're going to see one on exam. So these are important topics, and so we want to make sure that we all understand both of these. So let's pretend that you've got this reaction. Let's just pretend they're all aqueous. Okay. You've got 2x2, I guess it'd be better if they were gases, right? Diatomic gas. You've got 2x2 plus y2 is in equilibrium with 2x2y, right? So coefficient of 2 here, coefficient of 2 here. We haven't dealt with any ice tables yet so far that had coefficients, right? They've all been 1 to 1 to 1. We've never dealt with anything that had a coefficient before. So we haven't talked about what to do with a coefficient in an ice table. So let's pretend that you begin with a 0.5 molar concentration of both of your reactants, and I want to know what are the equilibrium concentrations going to be. Let's just talk about how we'd set up that ice table first. Notice this has to follow stoichiometry. Okay? Stoichiometry has to be obeyed. If the initial concentration is 0.5 molar of both reactants, that's just 0.5 and 0.5, just like we've always been doing. And this is 0, right? Because we're beginning with reactant, that means we don't have any product yet. Right, so the I is just 0.5, 0.5, and 0. Now, both of my reactants are going to go down by X. However, this reactant is going to go down by 2X. Why? We have to follow stoichiometry, okay? If there's a coefficient of 2, it gets distributed through my entire ice table, okay? So this is going to be 0.5 minus 2X. At equilibrium. Do you see why this is a 2 here? Because there's a coefficient of 2. If this were a 5, this would be minus 5x, and this would be 0.5 minus 5x. Okay? There's no coefficient here, it's just a coefficient of 1, so this is just regular old x, just like we've always done, 0.5 minus x. This is a coefficient of 2, so this is a product, it's going to go up, but it's not going to go up by x, it's going to go up by 2x. Right, so that equilibrium, that 2 gets carried all the way through. If this were a 4, right, this would go up by 4x. This would be 4x at equilibrium. Now, what about when I'm writing my K expression? What do coefficients do to my K expression? They make it squared, right? That 2 gets reflected in my K expression as well. So if I said, okay, K equals concentration of x2y, well, it's not x2y straight up, it's x2y squared because of that coefficient. And then it's not divided by x2, it's divided by x2 squared. And then this has a coefficient of 1, so it's just up to the first. Okay, so 2 things to keep in mind. Anytime your ice table has coefficients, whatever this coefficient is, 2, 3, 9, 100, whatever, right? That coefficient gets carried all the way through, so it gets put in front of the value of x. And thing number 2 to remember, that coefficient becomes the superscript in your K expression. Does this make sense? Okay, does this make sense? Law of mass action is why these coefficients become superscripts, and stoichiometry is why these coefficients get carried down. It's really important that you understand how to deal with a coefficient, because it's not only going to affect your algebra here, it's also going to affect your K expression here. And I didn't give you a value of K, I just made this up, right? So if we knew the value of K, we plug it in, solve our math, go about our business. Okay, does everybody understand how we got this? Is everybody cool on where this came from? We've got to distribute those coefficients, and then we've got to make them factor into our K expression. All right, so let's do this one together. H2 plus I2, both of these are gases, and they're in equilibrium with 2HI, which is also a gas, and equilibrium constant is 54.3, and I want to know what will the concentrations be at equilibrium if we begin with, 0.24 molar concentrations of both reactants. So H2 plus I2 in equilibrium with 2HI. All of these are gases. Equilibrium constant of 54.3. We begin with a 0.24 molar concentration. What are we going to have at equilibrium? So do we need an ice table? Can we do this without an ice table? No, we can't do this without an ice table, right? We've got to write an ice table. So we make our ice table, H2 and I2 and 2HI, right? Because these are all gases, so there's nothing that I can omit. So I tell you that the initial concentration of both reactants is 0.24 molar, 0.24 molar. That means that this is 0, right? What is my C row going to look like? What will go right here? Minus X. What will go here? Minus X. What will go here? Plus 2X. Good. Right? And then this just gets carried down. So my question to you here is, can we use the 5% approximation? No, we cannot. Why? Because K is greater than 1. When are we allowed to use the 5% approximation? K is less than 1. I can't tell you the number of people who use the 5% approximation when they shouldn't, right? Because if this is greater than 1, that means that it's reactant favored or product favored. Product favored. So that means that the concentration of this is going to change significantly, right? That means this is going to go down significantly. Yes, this is going to go down significantly. This is going to go up significantly. 5% approximation assumes that this is not going to go down very much. But because this is product favored, the only way that this can go way up is if this goes way down. Okay, so make sure you know, when can I use 5% approx, when can I not? When K is 54, you absolutely cannot be using the 5% approximation. Okay, so only thing new is distributing this 2, right? We can't use 5% approximation because this is product favored. Can't do it, don't go there, right? So we write our equilibrium expression, K is equal to concentration of HI squared. Why is it squared? Coefficient of 2, okay? So a lot of students make one of 2 mistakes. They either forget to carry the 2 through the ice table, or they forget to factor it into their K expression. Okay, you gotta do both. You gotta do both. If that coefficient were 3, what would this be here? 3 would be the third, okay? So now we plug in our value of K. We plug in our information from our ice table. 2x, quantity squared, divided by 0.24 minus x times 0.24 minus x. Since the numerator is being squared and the denominator is being squared, can I take the square root of both sides to reduce the math down so I don't have to solve the quadratic formula? Yes. If both of these are to the same power, squared over squared, well then I can just say, okay, square root of the right, square root of the left. What if the numerator was being squared and the denominator wasn't? I couldn't take the square root of both sides. I'd have to solve the quadratic formula, right? But since both the numerator and the denominator are both squared, life's easier. Take the square root of both sides. All right, so that means the square root of 54.3 is equal to 2x over 0.24 minus x. Do a little bit of algebra, and I get a value of x equals 0.189, which I then plug back into my ice table, and I get my equilibrium values. So this is evidence that I can't use the 5% approximation, right? Because you would expect my reactant concentrations to go way down if it's product favored. And it is product favored, and my reactant concentrations do go way down. And my product concentration does go way up. So my ice table makes sense in light of what my K value is, right? If K is a greater than 1, you would expect your equilibrium product to go way up, right? And you would expect your equilibrium reactant to go way down. So always make sure that your answer is reasonable in light of what your K value is. And always, 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 always ask yourself, when is it appropriate to use the 5% and when is it not? A lot of students love the 5% approximation because it takes out that nasty quadratic equation. Hey, that's great. I'm all up for simplifying your math, but you can only do it when it's appropriate, right? If K value is greater than 1, even if it's 1.1, right, or even if it's 1.03, you can't use 5% approximation. Okay? You good on how to do this one? Ready to try one for yourself? All right, you try this one. N2O4 is in equilibrium with 2 NO2. These are both gases. You begin with 1.5 molar concentration of the reactant. What will the equilibrium concentrations be if the equilibrium constant is 5.85 times 10 to the negative third? I'm going to pause the video, give you a minute to try it. Oops, and then we'll go over it. Zoom. All right, let's see what we got. So we begin with a 1.5 molar concentration. What are my concentrations going to be at equilibrium, given this equilibrium constant? So we're setting up an ice table. We're allowed to use the 5% approximation this time, right? Why? Why can we do that? Because is this reactant favored? Yes. K is less than 1. We can make the 5% approximation, right? So this is nothing new, right? There's nothing different here. In the 5% approximation, we assume that X is a number so small that at equilibrium, the initial and the equilibrium value are the same. So we're just going to plug this value in right here. This is 0. It's going to go up by 2x. So at equilibrium, the value will be 2x. All right, now we're going to do some algebra, right? We're given the, we need to write our K expression, right? NO2 squared, concentration of N2O4 on the bottom. Do we agree there? Yes? Don't forget to square it. Like I said, most students either forget to carry the 2 through here, or they forget to carry it into their K expression. Most common mistake I see is either forgetting to represent it here or forgetting to represent it here. So now we plug in our information, the equilibrium constant, 2x quantity squared, and then 1.5, right, because we're making the 5% approximation. 2x quantity squared is what number? It's 4x squared, right? So I multiply both sides by 1.5. 2x times 2x gives me 4x squared, right? That's a really trivial math thing, but I see this mistake a lot too. I'm not sure why, right? For some reason, a lot of students forget to square the 2. They'll square the x, but they won't square the 2, right? You got to square 2 as well as the x, right? 2x times 2x gives me 4x squared. Now we divide both sides by 4, take the square root, right? I get x is equal to 0.0468. But I need to make sure that I was okay in using the 5% approximation, that was something that I'm allowed to do. So how do I check my work to make sure that making this approximation was okay? Who remembers? You have to find the range, right? So we take 5% of our initial concentration, right? 5% is 0.05. So 5% of 1.5 is 0.075. And so our range is our value minus 5% all the way up to our value plus 5%, right? Now, one of these is obviously nonsense, because can this value go up if this value is 0? No, that can't make this. That doesn't make sense, right? Because how could this go up? Where would it come from? If this value is 0, it can't go up. But we always want to train ourselves to get in the habit of looking at both the positive and the negative, because what if this value isn't 0? Okay? In the future, we'll be doing ice tables where this value isn't 0. So we want to get in the habit of just looking at both the negative and the positive range, right? Because yes, this value is going to go down, right? But we just need to make sure it goes down by a range, by an amount that falls within this range. So my range is 1.425 to 1.575. So when I plug x in right here, I get 1.453, which is in that range, so we're good. So now that means I'm okay to plug x into my value here to get my final answer. So my final answer here, you can just leave that as 1.5. That's perfectly fine, because that was the approximation you made. And then there's your answer for NO2 concentration. Yeah?
Every time we do the 5% rule, we have to check it, or
99% of the time it works. Yeah. Any other questions on this one? If you made a mistake, just see who made it. Okay, let's talk about Le Chatelier's principle. That's a completely different can of worms. We're not actually going to do any ice tables in this part right now. Woohoo! We're going to talk about some concepts that we'll be using tomorrow in lab, actually. So here are some factors that can shift the equilibrium. And what I mean from that is, remember, equilibrium can lie on the reactants or it can lie on the products, right? You can have equilibrium on the reactant side, we say it's reactant favored. You can have equilibrium on the product side, right? We say it's product favored. I can manipulate my system so that the equilibrium from used to be reactant favored and now it's product favored, or vice versa. And the way that I can do that, remember, this means what? Change, right? Change. So I can change concentration. I can change pressure or volume if it's a gas. Only if it's a gas. Okay, this is not going to affect a solution. Changing pressure won't affect a solution. Changing volume won't change a solution. But it will change a gas. And I could also change the temperature. So if I have a reactant favored equilibrium and I want to make it product favored, I can manipulate my system to let me do that. And the way we do that is by using Le Chatelier's principle. Okay, change concentration, change temperature, that'll work for gases and solutions. But if you want to change pressure or volume, that's only going to affect gases, it's not going to affect solutions, right? Because if I do my reaction in a 50 milliliter beaker or a 100 milliliter beaker, right, that's not going to affect the solution. And same thing with the pressure here. But at a gas, that is a difference. That does make a difference. So what does Le Chatelier's principle say? It says if a system at equilibrium is disturbed by changing temperature, pressure, concentration of one of those components, now again, pressure only applies to a gas, the system will shift the equilibrium position to offset that disturbance. So if I'm at equilibrium and I come along and poke it, right, it's going to shift around to get back to equilibrium. That's what Le Chatelier's principle is telling us. So you can kind of think of it like a balance. And like I said, you can be a chemical bully, more or less. If you want your reaction to become reactant favored and it's currently product favored, you can use Le Chatelier's principle to drive the equilibrium to the side you want it to be on. So it's useful for us as well. So let's just look at this reaction. Now this is a graphic, okay? It's kind of a weak analogy, but it works. If you think of it like a balance. Here's my reaction, H2 and N2 in equilibrium with 2 NH3. Now we're not reflecting the coefficients here at all, okay? So that's why I say it's kind of weak, right? Because we don't have any coefficients here. We're just saying at equilibrium we've got H2 and N2, and it's in equilibrium with NH3, right? Now what if I increase the amount of one of my reactants, right? And make this box bigger. So I add extra H2. Okay, I'm in a gas situation, I have to like pump it in, right? I can't just pour it. But I'm pumping in extra reactant. Okay, now I'm heavy on this side, right? What's the only way to consume this extra reactant that I've added? Would I make more reactant? Would the equilibrium shift toward the reactant? Or would the equilibrium shift toward the product? What's the way to use this up, in other words? If I want to use this excess up that I've added, what do I do?
Add more.
Well, let's assume that we've added both. Now both of these boxes are too big. What's the way that I could use up this extra? If I make more NH3, right? So in other words, if this arrow goes further this way, then it does go back, right? We're shifting away from it. You see what I'm saying? How do I use up this H2 and N2? By making more NH3. So now I'm product favored. I've shifted the equilibrium, so now it's product favored. I'll actually make more NH3 so as to use up this extra reactant. So it's the opposite, right? If you add a reactant, the equilibrium is going to shift to the product in order to use it up. Does this make sense? Does this make sense? Because if I've got extra H2, well, I'm assuming I can't like vacuum it out, right? So the only way that I could use it up is by now becoming product favored, and now I've used it up, and now I'm back to everybody's box being the same. Does this make sense? Does this make sense? Let's look at another case. What if I remove some H2? How could I do that? Let's pretend that I add a substance that reacts with H2. Let's just pretend I add some O2 and I ignite it and I get some water, right? That would have some other ramifications as well, but let's just pretend for the sake of argument, I've added something that reacts with H2. It doesn't react with N2, so I've removed some of this H2, and now I've got a hole. Well, what do I do now? What's going to happen here? How can I get some of that H2 back? Just think about the law of conservation of mass. What's the only way that I could get this back? Is if some of this decomposes, right? If this reaction goes, in other words, if I become reactant favored, right? If I become reactant favored, now I get that H2 back, and now equilibrium is restored. Okay, so if you add a reactant, you shift the opposite direction to use it up. And if you remove a reactant, that's like digging a hole, you shift toward it. And the same would be true for the product. Let's pretend that I pump in some extra NH3, and now this value is too high. Well, what's the only way that I could get rid of this extra NH3? By breaking it down, right? If I now become reactant favored, that breaks it up, and now the excess that I've used is gone. Or likewise, if I add something that reacts with NH3, now it's gone. How can I get it back if these two react? Right? So you're going to do something to offset the change that you've done. And like I said, sometimes the way you remove a reactant is by adding a substance that reacts with it. That's what one of the things we're going to do tomorrow, right? Because you can't sit there and pick out reactant molecules or product molecules. That's not feasible. And one of the things you're going to do in lab to mess up your equilibrium and see what happens is add a substance that reacts so you can take it out. All right, now here's the important thing you need to remember in terms of K. If you alter those concentrations or you alter the number of moles, it's not going to affect K. It's not going to affect K. All right? And actually last week in lab, the simulation that you did, remember you did the calculations at 3 different concentrations, right? And you got essentially the same value of K. K is a constant at a given temperature, right? So if you manipulate those concentrations, that's not going to affect K. What does affect K? Who remembers? Temperature, right, good. So here's some data, okay? So here's the reaction, and here are the concentrations. You can tell I'm at equilibrium here. How? How do you know I'm at equilibrium? Is the graph interesting or is it boring? It's boring, right? This is not changing concentration. These concentrations aren't changing. But now, what did I do? N2 is the blue one, right? I've added some N2. So here in this transitional period, I add N2. What would I expect to happen to my equilibrium? If I add a reactant, equilibrium is going to shift to the reactants or products. Products, right? You would expect the amount of NH3 to go up. So when this goes up, hey, look at that, the amount of NH3 goes up, the amount of N2 goes down, right? So this is that transitional period where it's just figuring out what it needs to do. And now I'm at equilibrium again, right? But notice, K here is 0.297 and K here is 0.297. Right? So I've fleshed out my graph a little bit, but my value of K didn't change. Okay? So when you change concentrations, remember, the way to change K is not by changing concentration. The only way to change K is by changing the temperature. All right, let's look at changing volume or changing pressure. Now again, this only affects us if we're a gas or an aqueous substance. Who cares? Okay. And there are a couple ways that we can do this. We can physically manipulate the volume of our container, right? So if we're doing our reaction in a flask that's got a piston that you can move, right? That's something you can physically do to change the volume. Or maybe you add a gas, like a spectator gas, in other words. You're adding a gas that doesn't react. Helium's not going to do anything. It'll increase your total pressure, but it's not going to, you know, affect your equilibrium. I mean, it's not going to participate in this reaction. Okay, so let's look at both of these scenarios. So if we decrease the volume, we're going to shift the equilibrium to the side with the fewest number of moles. Fewest number of moles. Why? Why do you think that will happen? If we're in a smaller space now, do we want to have lots of moles or fewer moles? Fewer moles, right? Just think about it like this. Would you rather be in an elevator with one person or 12 people? I'd rather be in an elevator with one person, right? So if we have this reaction at equilibrium and I decrease the volume, now this is my sad, pathetic rendition here, so just bear with me, right? We're going to shift to the products because there's only 1 mole of product, but there are 2 moles on the reactant side. Okay? So we're going to shift to the side that will give us the fewer number of moles. Does this make sense? Again, just think about it in people terms. And then if we increase the volume, opposite, we can shift to the side with the greater number of moles. What if both sides have the same number of moles? Then there'd be no change. Okay, if it was 2 and 2, and you increase the volume or decrease the volume, no effect. What if this were AQ, and you change the volume? What would that be? AQ and AQ, and I change the volume? Nothing happens, right? It only affects if you're a gas. Does this make sense? Make sense? All right, now let's add a gas that's inert. In other words, we're treating it like a spectator, right? Because if it starts reacting with one of these, that's the equivalent of removing, and that's not what we're doing. Let's just say we're throwing in a gas that doesn't do anything, it's just hanging out in there. All right, so it'll increase the pressure. It's not going to affect equilibrium. Okay, that's the thing you need to know. These added molecules will make the pressure go up. Woohoo, congrats. But it's not going to affect the equilibrium. So if I add an inert gas, right, it's just a spectator. It'll make my total pressure higher, but it's not going to do anything to the equilibrium. Make sense? Make sense? We good on this one? Now, if you add something that starts reacting with these guys, obviously that's a different picture, right? Because that's the equivalent of increasing a reactant or decreasing a reactant. But if you're adding just a spectator, no effect. Okay, changing temperature. Remember, the equilibrium constant is temperature dependent. Yes, it is. So if we change the temperature of an endothermic reaction, that's going to be different than what we have when we change the temperature of an exothermic reaction. Because changing temperature is not only going to change the equilibrium position, it's also going to change the value of K. Okay, if I increase the temperature of an endothermic reaction, that will shift my equilibrium from one side to the other, and it will give me a new K. If I increase the temperature of an exothermic reaction, again, that will shift my equilibrium, and it will give me a new K. So far, we haven't done anything that affected K yet, right? We've only dealt with making a reactant favored, product favored, or a product favored reactant, but we kept our K. But now, once we start messing with temperature, we're going to get new K value. All right, so let's look at an exothermic reaction. Right? Exothermic means heat is a product. Right? If you are holding a beaker containing an exothermic reaction, the beaker would feel hot. Right? It's releasing heat. So you could think of heat as a product. Right? So if we're drawing our little schematic like we did a few minutes ago, reactants, products, and heat. Right? We're thinking of heat as an actual player here because it is. Right? If it's exothermic, heat is a product. All right, what if we increase the temperature? Now this piece is too big. So this is no different than increasing the concentration of this, wouldn't it? Increasing the temperature here, would that have the same effect as increasing the concentration of this? Yeah, it would, right? Because if I increase the concentration of this, what's it going to do? Shift that way to use it up, right? If I increase the temperature, how do I get rid of that extra energy? Go the other way, right? Break this down, use it up. And now my equilibrium is now on which side, reactants or products? It's on the reactant side, right? shift away, right? So I've forced it to now become reactant favored. So let's pretend that I am wanting to have lots of H2 and N2, and I don't want any NH3. I don't want it. It's not something I'm interested in. I want lots of H2 and N2. Well, if I just increase the temperature, there we go, I get what I want, and I'm happy as can be. Now, if we increase the temperature, this is exothermic, we have shifted the equilibrium to the reactant side. Why is K going to decrease? Why is K going to now go down? You don't need to memorize this, you know, like, oh, I got to memorize, what does K do, what does K do? If you can just talk yourself through the math, right? You don't need to memorize what's gonna happen to K, what's gonna happen to K, right? Because if K is concentration NH3 over concentration of H2, concentration of N2, I've shifted the equilibrium this way, right? These numbers are now gonna be bigger, right? These numbers go up. So let's pretend that it used to be 1 over 2, and now it becomes 1 over 8, which is a bigger number, right? K went down because my denominator got bigger. So, I mean, yes, you can memorize, okay, if I increase the temperature of an exothermic reaction, that decreases the value of K. That's a lot of memorization because you're going to have to memorize what happens to K when you decrease the temperature, what happens to K when you increase the temperature for both exothermic and endothermic. So basically you're memorizing 4 bullet points. Or if you just know, okay, K comes from reactants and products over reactants, and if I shift one way or the other, right, I'm going to get a new K. Does this make sense? Because remember, K is temperature dependent. Does everybody understand why K is going to decrease? Everyone understand why K decreases? Again, K is temperature dependent. Now, if we decrease the temperature of an exothermic reaction, right, this value goes down. So which way is the equilibrium going to shift? Toward the reactants or towards the products? If this value goes down, what's the only way I can get that energy back? By making more of this, right? The equilibrium is going to shift to products. Okay, well, K is going to increase then, because, right, if the numerator gets bigger, then by definition, K is getting bigger. Does this make sense? Is everyone with me? All right, and then endothermic is just the opposite. Endothermic would be the opposite. Heat has to be thought of as a reactant, right? Reactant means endothermic. Heat's going in. Right? So this is a pretty boring equilibrium expression because I've got 2 solids. So nonetheless, heat is a requirement here. So if I increase the temperature, what's going to happen? Is the equilibrium going to shift to the products or towards the reactants? If this goes up, what's the only way to get rid of it? Shift away from it, right? It'll become product favored. And that again is going to make K go up, right? Anytime the numerator gets bigger, anytime the products gets bigger, K is getting bigger, right? Anytime the reactant's getting bigger, K is getting smaller. And then decreasing, it's the opposite, right? If I decrease this, I'm shifting away from the products, right? And so we're going to get a smaller value of K. So a summary of Le Chatelier's principle is that K is only going to change if we alter the temperature. If we're just playing with concentrations, it's going to give me a product-favored scenario versus a reactant-favored scenario. Woohoo! But I'm not going to get a new K unless I start messing with temperature, which is what I just said. Okay, so I can force a reactant-favored equilibrium to become product-favored, or I can force a product-favored reaction to become reactant-favored by playing with my concentrations, and that's not going to give me a new K value. The only way I'll get new K is if I start adjusting temperature, because K is temperature-dependent. Is everybody good on these concepts? Make sense? Okay, so I'm going to pause the video, and I want you to try these. I need to make some space here so it's easier to read. All right, so try these problems. Pause. All right, let's go over these. So we're looking at what's going to happen to the equilibrium position based on these modifications. If we add O2, are we shifting towards the products or are we going to shift towards the reactants? If we add O2, will we shift to the products or shift to the reactants or no change? We shift towards the products, right? Because what's the only way to consume this? Make more product, right? So we'd shift to the products. What if we remove H2S? Shift to the reactants, shift to the products, or no change? If I have dug myself into a hole, what's the only way to fill that back in? If the equilibrium goes towards the reactants, right? How do I get this H2S back? These two things have to react and give it back to me, right? So this would cause equilibrium to shift towards the reactants. All right, remove H2O. Shift to the products, shift to the reactants, or no change? Shift to the products, right? How do I get that water vapor back? By shifting the equilibrium this way. What if I add sulfur? No change. Why? It's a solid. Good. Okay, I'll pause the video and then you try these. Predict what direction the equilibrium will shift when the volume of the vessel is decreased. Resume. Let's see what we got. Okay, when we're dealing with volume changes, there's something important to consider. What kind of substances are affected by volume changes? Gases. Are aqueous species affected by volume changes? No, they're not. Okay, so for A, the volume is decreased. Is it going to shift to the products, shift to the reactants, or no change? Shift to the reactants, right. Why? Fewer moles, right. 1 mole versus 2 moles. Good. What about B? Now be careful with B because there's something we need to worry about in B. We've got 2 solids, right? So we're not looking at them. So we're comparing 3 versus 2. So which side, reactants or products? It shifts to the products, right? Because this is a solid, this is a solid. We're not looking at them, we're only looking at the 2 gases. 2 versus 3, so equilibrium will shift to the products. And what about C? What happens there? No change, right? Because I've got 2 moles on the products, I've got 2 moles on the reactants, so no change. Good. Any questions on this one? I think that's just the answers. Yep. All right, let's talk about a catalyst and what it does here. A catalyst will let us come to equilibrium at a faster rate, but it's not going to change the equilibrium constant. Okay, so in terms of Le Chatelier's principle, if you throw a catalyst in there, I can come to equilibrium faster, but I'm not gonna get a new K. And so that's just to summarize what I just said. K is not affected by using the catalyst. It's not affected by the catalyst. All right. So there's just a different, and 2 graphs to show that, right? I've got uncatalyzed versus catalyzed, different activation energy, right? But my K value, which comes from these 2, is not changing. All right, got a few more practice problems for us to do before we're done today. Predict what will happen to K, if anything, when we increase the temperature for the following reactions. The first one is endothermic. The second one is exothermic. I'm going to pause the video, give you a minute to try it. let's go over this one. Okay, now again, you can sit around and memorize increase the temperature of an endothermic reaction does blah, blah, blah to K. You can memorize that as 4 separate pieces of information in your brain. You obviously have that freedom. But I think the easier way to go about doing it is if you just know how to get K and you know some Le Chatelier's principle, you can reason your way through the answer. So this is endothermic. Is heat to be thought of as a reactant or as a product? Endothermic. Heat is a reactant. Okay, so let's just imagine the word heat right here. And we increase that reactant, so to say. What's going to happen to the equilibrium position? Will it shift to the reactants or shift to the products? It'll shift to the products, right. Equilibrium's going over here to the product side. So in my K expression, which value is going to get bigger, the numerator or the denominator? The numerator, right? Because it's products over reactants. So if this numerator, if the numerator gets bigger because my equilibrium is now over here, does that give me a bigger value of K or a smaller value of K? Let's think about it this way. It used to be 10 over 2, and now it's 100 over 2. It gets bigger, right? K is going to increase. K would increase. You see why the answer is K increases? All right, let's do this one. Exothermic. When we're dealing with an exothermic reaction, do we think of heat as a reactant or as a product? And this is a gas, by the way. We think of it as a product, right? So if I increase the product, in other words, this concentration of heat, so to say, goes up, is the equilibrium going to shift to the reactants or to the products? To the reactants, okay? K is products over reactants. So which just got bigger, the numerator or the denominator? Denominator. So we went from 1 over 4 to 1 over 20. Which number's smaller? Right, the value of K went down. So K would decrease. K increases here, K decreases here. Do we understand how to do these two? Again, you can memorize it. You can sit down and memorize it. If it's endothermic and I increase the temperature, this is what happens to K. You can memorize it. And that's well within your rights. But I think if you just talk yourself through it, you don't have so much stuff to memorize, right? Plus, if you don't have to memorize stuff and you understand how it works, it'll make your overall understanding of equilibrium better. My opinion, take it or leave it. All right. Here's another one for you to try. We've got an equilibrium reaction up there at the top. Explain how each of these changes would affect equilibrium, if at all. This problem. Okay. If we add N2O4, do we shift to the reactants or shift to the products? What's the only way to get rid of the extra N2O4? Is if it breaks down, right? So I shift to the reactants. If I add NO2, what happens? What's the only way to get rid of that extra? Shift to products, use it up, right? What if I remove N2O4? Now I don't have any product. How do I get it back? Shift to products, right? In other words, this has to break down. And then if I remove NO2, I don't have any NO2 anymore. Shift to reactants. What will happen to K in all of these? Stays the same, right? Why? Because I am not changing temperature. Good. Good, good, good. All right. Last one. I think it's the last one. Talking about volume here. I'll pause the recording and let you try it. All right, last one to go over. Same reaction. Now we're just changing the volume. Changing the volume only affects what? Solids, liquids, gases, aqueous what? Gases, right. So if I decrease the volume, are we shifting to reactants or shifting to products? Products, why? Fewer number of moles, right. And if I increase the volume, I shift to the what? Reactants, right? Greater number of moles. Does K change in either one of these scenarios? No, it does not. Good. Okay, that's where we're going to stop for today. So I will see you tomorrow for lab. Have a good day.